Okay, so here is some questions on proving that or investigating whether events are independent. So I'm going to work through some of these. If you still have questions after it, please ask. So question 2, a family has 3 children. A is the event that the family has at most one boy. So at most one boy would mean they have no boys or one boy only. Okay, B is the event that a family has children of both sexes. So that would mean that it can't be all boys. So can't be boy, boy, boy. Okay. Now, the first thing I have to do is find out how many possible outcomes there are. So I have a family has, a family has 3 children. Okay, now, so they've got 1, 2, 3 children. Their first child can be a boy or a girl. Their second child can be a boy or a girl. And the third child can be a boy or a girl. So I'm not told there's any specific criteria. And they're having all 3 children. So 2 by 2 by 2. There are 8 outcomes. Okay, of the total different ways that they could have their children. So I'm asked to calculate PA and PB. So the probability of A is at most one boy. Okay, so we said that there was no boys or one boy. So there's a couple of different ways you can do this. But if there is no boys, then it is girl, girl, girl. And at most one boy, the boy could be the firstborn, and then there could be 2 girls afterwards. You could have a girl born and then a boy and then another girl. You could have 2 girls born and the boy being the youngest. So there are 4 options or 4 outcomes here out of the total of 8. So the probability of A is a half. Okay. The probability of B then is that there's children of both sexes. Okay. So the only ones that we can't have girl, 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 or boy, boy, boy. But every other outcome has a mix of sexes. So there are 6 other outcomes out of the total of 8. Okay, so the probability of B is 3/4. Okay, the probability of A intersection B. Okay, this would be the probability that at most there is one boy. So at most one boy, and they have to be of both sexes. Okay, so from probability A, we know that to have at most one boy, there's 4 outcomes. There's girl, 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 boy, girl, 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 boy, girl, 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 boy. But if they have to be of both sexes, well then the girl, 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 we can't count. So there are 3 remaining choices. Okay, from up here. So there are 3 out of 8 remaining choices that could be A intersection B. Okay, so to prove these events are independent or not, we take the probability of A, multiply it by the probability of B. So I've got a half times 3/4, which gets me 3/8. Okay, which is equal to the PA intersection B. So these 2 events are independent. Okay, that proves that they are independent, because when I multiply the probability of A by the probability of B, I get my A intersection B. Okay, question 3. 3 cards are selected at random. Now, I love this word selected or chosen, because that means that there is choice. So that means that you are using that C function on the calculator. okay, at random from a standard pack of 52 cards. So there are 3 chosen from 52. So 52 cards, choose 3. Okay, that means there are 22,100 outcomes. Okay, possible outcomes of choosing 3 cards at random. E is the event that we get 3 kings, and F is the event that we get exactly 1 heart. I'm asked to calculate PE and PF and then find the intersection to investigate if they're independent. Okay, so question 3. I have that 52 choose 3 already is 22,100. I'm now looking for the probability of E, okay, which is that all 3 cards are kings. Okay, so the probability that all 3 cards are kings, I would have to choose 3 from the 4 kings. Okay, there are 4 kings in a pack, so I'm choosing 3 from 4. That will get me 4 possible outcomes out of the total 22,100. Okay, the probability of F then. Okay, the probability of F is that there is exactly 1 heart. And if there's exactly 1 heart, then the others, so and the other 2 from different suits. Okay, so exactly 1 heart, I have 13 hearts in total. I'm choosing 1. Okay, so if you're putting that into your calculator, it'll be 13, choose 1. And, so and is multiply. There are 39 other cards that are not hearts. So if I take the 13 out of the 52, there are 39 other cards, and I have to choose any 2 of them. Because my only criteria here is that exactly 1 is hearts. The other 2 can be anything else. So any 2 from the other 32. Okay, and again, if I'm putting that into a calculator, it's going to be 39, choose 2. Okay, multiply those 2 outcomes and you'll get 9,633. And you're thinking this actually is going to be quite a big outcome, okay, because you're allowed to pick completely any 2 other cards that are not a heart, okay, and you're choosing one of 13 hearts. Okay, so that makes 9,633 over 22,100. I'm then looking for PE intersection F. Okay, so the probability that E and F happen together. So they have to be 3 kings. And one of those kings, so 1 card, and in this case it has to be 1 card that's a king because all 3 of them are kings. So 1 card, the king is a heart. Okay, exactly 1 card has to be a heart. Okay, so if exactly 1 card has to be a heart, there is only 1 king of hearts. So there's only 1 option for that. Okay, and the other 2 cards are chosen from the remaining 3 kings. So now 1 king is chosen, the king of hearts is chosen. So now I have the king of diamonds, spades, and clubs left. So I've got 3 of them left, and I'm choosing any 2 from that 3. Okay, so that's from your diamonds, clubs, and spades. And you're choosing 2 kings from that. There is only 1 king of hearts. Okay, that leaves me with 3 outcomes in total out of 22,100. All right, I just want to get another page here. Okay, so now I want to prove that the probability of E times the probability of F. Okay, so I'm going to find that. So the probability of E up here was 4 over 22,100 multiplied by the probability of F, which was 9633 over 22,100. Okay, in multiplying those two, I will get 57 over 722,500. So it's a massive number. Okay, that does not equal my 3 over 22,100. That was my PE intersection F. So in this case, these are not independent. Okay. Right, question 4. Okay. Question 4 says, let A and B be events such that PA is 1/4, PA union B is a third, and be careful, that's union, not intersection, and the probability of B is P. Find the value of P if A and B are independent. So we know they are independent this time. So there's a couple of things here, because if I know they are independent, okay, I know that A and B are independent. So therefore, when I multiply the probability of A times the probability of B, that will give me the probability of A intersection B, because they are independent. So I take 1/4, which was my probability of A, multiplied by P, which is my probability of B, and that gets me P over 1/4, which is my probability of A intersection B. And I have another formula that says that the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersection B. Okay, remember that's for independent events. Okay, and I know all of my stuff here. I'm given a third, I'm given 1/4, I'm given P, and I found P over 4. Okay, now multiple of the bottom line, or highest or lowest common multiple of the bottom line is 12. So multiply everything across by 12 to get rid of the fractions. A third by 12 is 4. 1/4 by 12 is 3 plus 12p, and 12 divided by 4 will give me 3p. Okay, and by simple algebra, you will get that p is equal to 1/9. Okay, so the probability of B is 1/9. Okay. Okay, question 5 then. Question 5, let A and B be independent events. So again, I know that A and B are independent. I'm given the probability of A, and I'm given the probability of A union B, and I'm asked to find the probability of B, given that A has already happened. Now remember, because I know that they are independent, then I know straight away that the probability of B, given that A has already happened, has no effect. A has no effect on it because they're independent. So that is same as finding the probability of B. So really what I'm asked in this question is to find the probability of B. And this is really just understanding your formula, understanding what events, what A and B being independent would mean, and understanding your conditional probability with respect to independent events. Okay, so that bit there is really important that I've started. Okay. Going down here, so question 5. You have the probability of A is 1/2. And we were given that the probability of A union B is equal to 2/3. Okay. Now remember, you know that they're independent. So you know that the probability of A intersection B is equal to the probability of A times the probability of B. Now ultimately, remember, this is actually what we're looking for. So the probability of A intersection B is equal to the probability of A, which we know is 1/2, times the probability of B, call it whatever you want. I'll give it small number B. Okay, or I can give it an X, or I can give it a Y. I'm going to stick with B because I'm looking for the probability of B. Okay, so the probability of A intersection B here is equal to B over 2. All right, now remember that's a B, not a 6. Okay, I'm just going to make that a little bit more obvious. Okay, so a B over 2. And I also know, if they are independent, that the probability of A intersection B is equal to the probability of A plus the probability of B minus the probability of A intersection B. And I'm given all of these. I've got 2/3 is equal to 1/2 plus B minus B over 2. Multiply across by 6 to get rid of the fraction. So 2/3 by 6 is 4. 1/2 by 6 is 3. Plus 6B minus 3B. And by simply solving this, you will find that B is equal to 1/3, okay, which is probability of B is 1/3. And because the probability of A has no effect on the probability of B, the probability of B, given that A has already happened, is also 1/3. Okay. Okay, next question is question 6 here. Show that if the probability of E, given that F has already happened, is equal to the probability of E, so it's an independent event, so E and F are independent, then the probability of F, given that E has already happened, is equal to the probability of F. So in other words, if they're an independent event, it doesn't make any difference whether it's E given F or F given E. Okay, assuming neither is 0. Okay, I'm going to insert my page. Sorry now. We're having a few technical difficulties. Calm down. Okay, so question 6. We have the probability of E, given that F has already happened, is equal to the probability of E. There's a couple of different ways that you can go about this, okay, because you know they're independent. So there's a couple of different ways I can look at. First of all, I can look at this, okay. If I know that the probability of E given F has already happened, I can write that as the probability of E intersection F is equal to the probability, probability of F. Okay, I don't know what's going on here. Okay, it doesn't want to write there for some reason. Okay, the probability of F, right, that should be there, is equal to the probability of E. Okay, therefore, by cross multiplying, or by some simple multiplication rule here, okay, I have that the probability of E times the probability of F, okay, is equal to P intersection F. Now, I actually could have written that at the very start anyway, because I know that they're independent. So I actually could have written that regardless, okay, without having to do the work to get it. But then I also know that the probability of F, given that E has already happened, is equal to the probability of E intersection F over the probability of E. And that would have to equal F, okay, because I'm told this. But then the top line, okay, is my P intersection F, which is this. So PE times PF over PE proof done. PF is equal to PF. Okay, right, my very last question then. Question 7. I'm going to scroll back up. Okay, a group of 7 women and 5 men go hill walking. So first of all, that's 12 people. Okay, go hill walking. 4 of the women and 2 of the men are from Cork, and the rest are from Kerry. 2 of the group are chosen at random. So if 2 of the group are chosen at random, that is 12, choose 2. Or onto your calculator, 12, choose 2. So straight away, 12, choose 2, I'll get 66. Okay? Let E be the event that the 2 chosen are from Cork. So both chosen are from Cork. Okay, so I have 6 people from Cork, and I'm going to choose 2. So I have 6 people from Cork. The probability that I choose 2, I've got 15, and that's over my 66. Okay, because I have 15 out of a possible of 66 selections. 15 of those selections could come from Cork. Okay, let F be the event that the 2 chosen are both women. Okay, so there are 7 women. So I have 7, choose 2. So the probability that they are both women, okay, 7 choose 2 is 21. So the probability that they are both women is 21, again, over 66. There are 66 total options for choice. And my question is, investigate if E and F are independent. Okay, so I'm going to go down here to give myself some more room. Okay, so as we've just said there, question 7, the probability of E, that they're both from Cork, we said we had 6 choose 2, so it was 15 over 66. The probability that they were both women, we had 7 women, we were choosing 2, that was 21 over 66. Then the probability of E intersection F, okay, that means that there are 2 from Cork and these 2 are women. Okay, because they have to be both from Cork and women. There is 4 women from Cork, and I need to only choose 2 of them. So 4 choose 2. And again, on your calculator, that is 4 choose 2. Okay, so 4 choose 2 is 6. And again, if I write that as a probability, it's 6 over 66. Okay, then I've got my probability of E multiplied by my probability of F. Okay, if they are independent, then that will equal my probability of E intersection F. So it will equal 6 over 66. So my probability of E was 15 over 66. My probability of F is 21 over 66. Multiplying those together, I get 35 over 121, which is not equal to 6 over 66. So it is not equal to my E intersection F, and therefore these events are not independent. Okay, so these are just other ways as well. Remember, you also have your proving independent using your conditional, okay, which is on the other notes. So make sure you have a little look back through them also. Okay, the most important thing to remember when we're proving that events are independent is actually this here, okay, is that if you multiply the probability of one by the probability of the other, if they are independent, it will get the probability of E intersection F. If it doesn't get the probability of E intersection F, then they are not independent.